Hi, good afternoon.
Hello, how are you, sir?
All doing good. Thank you so much. How about you?
I'm fine, thank you. We have with us here Professor Brejesh Lall, Professor Arzad, and team from TCS, Mr. Swarnava Day, Mr. Chandan, and Mr. Ayan. Shall we start?
Was that a question for me?
No, for everyone actually. Alok and Mr. Arun. Shall we begin? Okay. Good afternoon, everyone, and welcome. We have this workshop today for the 2022 ITU AI/ML Challenge. The topic for this workshop is AI/ML driven low latency closed loop control, wherein we have some eminent speakers from academia as well as industry who would be telling us about various aspects of haptics communication and tactile internet. The agenda for the workshop is as displayed here. Beginning with an introduction, we have the speakers giving us more details as to how the haptics communication has evolved and what all are the architecture and protocol perspectives, etc. The main principal investigator of this activity is Professor Brejesh Lall, who is presently a professor in the electrical engineering department at IIT Delhi. Professor Lall completed his PhD in 1999 from IIT Delhi and worked at Hughes Software System in September 97. Thereafter, he came back and joined IIT Delhi as a faculty member. The areas in which he has been publishing and carrying out his research include signal processing, machine learning, computer vision, etc. He has been coordinating two centers of excellence at IIT Delhi, Airtel and Ericsson, and he has also been the co-PI of the Building 5G testbed funded by DOT. I now request Professor Brejesh Lall to kindly welcome the audience and the participants.
Thank you, Pimi. Good afternoon, everyone, and welcome to this workshop. It's a pleasure to have all of you here participating and attending this particular workshop. The other good thing is that after a long time, it's in hybrid mode, which means that we have some people, though very few in the room with me. We've gotten so used to people attending workshops online, conferences online, that it's always a pleasure to see other humans in the room. Back to the subject. So as communication evolves, as technology evolves, what is happening is the human beings start expecting more and more from the technology and what these applications are able to offer to the person. So of late, there has been a great increase in demand vis-a-vis the quality of service that such kind of applications offer, especially communications. Now, communications became very, very commonplace, mainly because of 2 years of COVID, where people had to work and get and communicate and connect online. So because of that, there was a huge thrust on communications. We realized what are the things that we've done well over the last few years. And we also realized what are the few things that stand to be accomplished still. So out of these understandings comes the need to include haptics in our communication paradigm, or the way we communicate with each other. So immersion in and shared experiences is a term that we heard a lot of during the COVID days, and haptics is central to enabling some of that happening. So as far as haptics is concerned, there are 3 or 4 kinds of works that need to be done to bring this technology to maturity. One, of course, is building devices, the endpoints which are capable enough to do some of the things that we expect them to do. So there'll be 2 types of devices here, some which will be actuators, which means they will do things that we expect them to do, and the others will be sensing kind of devices, which will be able to look at the immediate environment, sense it, and communicate whatever they've understood to possibly a remote location from where decisions could be taken. So this is one aspect where haptic endpoints research will continue. Middleware for such devices is another area where people will continue to focus on. And finally, the need to integrate it with the communication architectures, the networks that are being built by various organizations and standardization bodies all over the world. And the last area that is going to play a critical role is AI/ML. So artificial intelligence and machine learning has come a long way in the last 7 to 8 years. And some of it will now find its way into further strengthening the offerings of the haptics as a technology. In light with this, we've come up with this idea of a build-a-thon, a hackathon that we've come up with to get participants to share their ideas in the way they can handle haptics better. The goal of the group here at IIT Delhi, along with our collaborators in IIT Bhilai, is to understand haptics as a modality better and integrate it better with the communication environment. To this end, MEC plays a key role. The multi-access edge computing element that has become quite popular with the advent of 5G is something that allows for low latency applications to run easily and rather conveniently on networks that we're deploying. So what we are trying to do here is bring MEC along with haptics together in the form of two interesting problems that, of course, the other speakers are going to detail out in the presentations later. So I won't spend time on that. Rather, I would expect that people participate and come up with new ideas, come up with better and more optimized ways of achieving the goals. What we intend to do is share simulated data with you and possibly some emulated data. And the team that shows the most promise in terms of practical deployability will be offered a chance to come to IIT Delhi, work in the lab on actual hardware and sort of showcase their solution to the rest of the world. This is part of the ITUT initiative, and I thank Vishnuji for that. So, and Arun Mukherjee, who've helped us make this thing a reality. And some of the participants, I think the winners, you'll get to know more details about that. We'll get a chance to participate in the global round for this particular activity. So, so I would like to end this introduction by thanking all the eminent researchers who've agreed to give expert talks. I'd like to thank the registrants who've shown interest in participating in this particular build-a-thon, and the other audience who've come here to listen to what the experts have to say about haptics as a technology and how it's going to be integrated with the network architectures that exist today. Welcome again, everyone. Wish you the best. Hope you have an enriching workshop. Thanks.
Thank you, Professor Lall. Our first speaker is Professor M. Manivannan from IIT Madras. He has received his postdoctoral training from MIT Cambridge and was a visiting scientist at MGH of Harvard Medical School in Boston. He has also been a visiting faculty in CMC Vellore. Before that, he received another postdoctoral training at National Institute of Standards and Technology. He was serving as a chief software architect at a spin-off company of MIT Touch Lab in Cambridge. In 2005, Dr. Manivannan has set up the first Touch Lab in India at IIT Madras, which is called as the Haptics Lab. He holds a PhD and ME degree from ISC Bangalore and is currently working as a professor in the Department of Applied Mechanics at IIT Madras. I welcome you, sir. Kindly enlighten us with the topic on haptics communication and how the touch feedback and the applications work. Can't hear you, doctor. Professor, you're on mute. Mr. Alok, can you please check what's the issue? Professor Manivanan, am I audible to you? Since we are having issue connecting with Professor Manivanan, Dr. Vineet, will you be able to carry the talk forward?
Yes, I was actually expecting a few talks ahead of mine to introduce haptic communications and tactile internet in general. But since this is pretty much on demand, I think I'll be able to give it a go. No problem.
Thank you so much. So Dr. Vineet is basically a postdoctoral researcher from Delft University, Netherlands. I'm sorry, my screen is giving some issue right now. He did his PhD from IIT Bombay in the area of tele-haptic communication over a shared network. And in the past, he has worked as a software engineer at Infosys Technologies. He has also worked as an assistant professor at the University of South Bohemia, Czech Republic. He has published his work with regard to haptics communication and tactile internet in reputed journals and conferences, and also is a standards committee contributing member of IEEE P1918.1. Dr. Vineet, kindly address the audience and let us know more details about the tactile communication and 5G and beyond, specific to the architecture and protocols.
Thank you so much, Pimi, for the kind introduction. Let me start off by sharing my screen.
Good afternoon. Am I audible?
Yes, sir, we can hear you.
Thank you.
Should we then wait for Dr. Manivanan to finish his presentation and then I chip in later?
No, sir, I think you can start. After that, we'll follow up with Professor Manivanan. Is that okay, Professor?
How long is it going to take?
15-20 minutes.
15-20 minutes, is it? Should be fine. Yes, please go ahead.
Thank you. Over to you, Dr. Vineet.
All right. Thank you so much. Probably I'm sharing the wrong screen. Give me a minute, please. All right. Is my slide visible?
Yes, sir.
Excellent. All right. Thank you so much for the kind introduction. I work in the area of tactile internet, which is essentially a communication of tactile signals as effectively as possible. And we do have a group here at Technical University Delft, which is active in many fronts of tactile internet. So in this presentation, I'm going to be specifically focusing on the communication aspect of it, and of course, a few more aspects that go beyond communication. And that's the reason the title says 5G and beyond. Okay, so like I mentioned earlier, I was expecting the audience to already have a bit of background in tactile internet, given that there were at least two talks scheduled ahead of mine. But now, since I'm the first one for the day, it probably makes sense to talk a bit more about tactile internet than what was planned. So tactile internet is a set of sensing, networking, and actuation infrastructure that deals with effective communication of what is called tactile signals or haptic signals over the internet. So here is the idea behind tactile internet. So there is a master domain here, which hosts the human operator. And the intent of the human operator is to effectively teleoperate in what is called the control domain. In order to do this, the human operator is equipped with an exoskeleton, which is the blue device that you see here strapped on the hand. And this exoskeleton, which is also called the haptic device, captures the kinematic information associated with the movement of the hand. And typically, this kinematic information is nothing but position of the hand, as well as the velocity with which the hand moves, as well as some orientation information. This kinematic information is then communicated to the control domain, where you have a robotic arm or a robotic hand, which tries to replicate the human movements as precisely as possible. And it is in this control domain, there are a few physical objects, possibly, which the human operator tries to interact with or even manipulate. So when the remote robotic arm sort of replicates the human movements, and if the human intends to, let's say, grasp a physical object in the control domain, so the robotic arm also mirrors that motion. And when the robotic arm grasps a physical object, the force feedback, which is generated as a result of collision or contact between two physical objects, is captured by force sensors on the robotic arm. So the force which is captured is also called haptic feedback. And this haptic feedback is transmitted back from the control domain to the master domain, along with video information, so as to enable the human operator to seamlessly manipulate the remote environment. So as can be seen, tactile communication is a two-way communication involving kinematics, haptic, and video modalities. All right, so a very challenging requirement of tactile internet, which is very different from conventional audio and video communication, is its ultra low latency requirement. So what we mean by ultra low latency requirement is that from the moment the human operator makes a certain motion to the time instant, the corresponding haptic feedback gets to the operator. So the round trip latency should have ultra low latency features. And this ultra low latency is typically estimated to be lower than 5 milliseconds. This is a huge challenge because the current networks are designed for audio video sort of communications, which have much higher latency requirement than what haptic communication pitches. So with that ultra low latency challenge in mind, let's move ahead with what are the practical issues with deploying tactile internet applications. Eventually, tactile internet application is to do with keeping the operator happy with teleoperation. And of course, users' perception and response is very subjective. So different human or different human operators might have different perception and different responses to the same stimuli. So keeping the human operator happy is quite a challenging task in itself. Adding to this complexity is also the heterogeneous levels of dexterity with which humans perform any physical action. So in general, human interaction with any physical object is very complex to model, and it involves an intensive investigation spanning a wide variety of research domains. However, the essence of tactile internet is to keep the human operator happy, because if that happens, by keeping the human operator happy, I mean to provide a satisfactory performance to the human user so that he or she can perform the intended operations in the control domain as if it were to be done right where the human is located locally. So it's very important to have a satisfactory or good user experience in order for tactile internet to really thrive. So in this presentation, I'm going to be focusing on three main themes related to tactile internet. One is related to actually physically communicating the tactile signals or the haptic signals itself. And once we have tactile internet solutions in place, we also need to quantify how these solutions are performing in terms of how well can they provide satisfactory or good user experience. So we need some measurement tools in place that can quantify the performance of tactile internet. And finally, because we are talking of network infrastructure, network latency and packet losses are inevitable. So the idea is to live with these network latency and packet losses and do a bit more in terms of effective signal reconstruction so that any live or mission critical applications like telesurgery or even remote disaster management that tactile internet can enable can run smoothly. So let's start off by talking about the communication challenges. So like I said earlier, audio video teleconferencing applications have a much higher latency requirement. Typically, audio has about 100 milliseconds, which means it's okay even if the round trip latency in a typical teleconferencing application, it's okay even if it's about 100 milliseconds. And that's because when we speak, we use our own speech and our own auditory system as feedback. So even if the latency of the network is high, we have local feedback running right here. So even a high network latency doesn't really hamper our own ability of speaking. However, with tactile internet, the user is performing some motions and expecting a haptic feedback from the control domain, which of course takes time. And keeping this round trip latency very low or having a fast tactile loop is crucial, because only a fast tactile loop can enable effective tactile internet operation. So of course, an obvious solution is to improve the network infrastructure as much as possible, make as many optimizations as possible to satisfy the tactile internet requirement of ultra low latency. So let's start off by taking a concrete use case of tactile internet, which is a connected factory that can enable Industry 4.0 revolution. So what happens in a connected factory use case is that there are several mobile tele-robots in an industry site where the intention is to run a lot of industrial tasks, such as, let's say, repair or actively running an industrial process. And that is done by remotely controlling these robots by humans located in the master domain that's far off from the actual industry. And since these are mobile robots, they are wirelessly connected to an access point or a base station. And then there is a core network domain, which is responsible for transporting the haptic signals over long haul networks. A lot has already been done and is also underway in terms of improving the core network domain in terms of software-defined networks, 5G ports, and network function virtualization, and so on. So in this particular work, we focus on the first or the last mile communication hop, which is a wireless network. And we focus on Wi-Fi networks for this particular work because modern Wi-Fi systems, such as the recent Wi-Fi 6 or the upcoming Wi-Fi 7, are tending more and more towards providing support to ultra-low latency applications. So the objective of our work is how do we tune the existing Wi-Fi networks and also provide algorithms to upcoming Wi-Fi systems such that they can indeed provide support to tactile internet type of application. Like we talked about earlier, there is a kinematic stream going from master domain to the control domain. And there are two different modalities going from control domain to the master domain, which is haptic and video. And we have already seen that video has much higher latency requirement than haptics, which is about sub 5 milliseconds. So how does the state of the art deal with handling this multiple modalities being generated by the same source? So let's say there is a robotic arm here, and attached to the robotic arm is a camera system as well as force sensors. The force sensors generate continuous haptic stream as well, and the camera generates continuous visual feedback or video stream. So what the state of the art in tactile internet does is at the application layer, it has two different modalities coming in. And the application layer sort of merges these two streams, packetizes them together, and pushes them downstream the networks. And the MAC layer is then responsible for orchestrating the channel, basically communicating the packets over the physical layer. So what the problem with this approach is that two different modalities with heterogeneous latency requirement, one with sub 5 millisecond and one with at least an order of magnitude higher, they are merged together to generate a single packet stream. So, so the problem with this is the moment we have multiple modalities being packetized together, there is no or there is lack of opportunity to prioritize haptic stream over the video stream. Because whenever one wants to send out haptic packets, video packets or video data inevitably get transmitted. And whenever one does not want to, let's say, or one wants to postpone video transmissions, haptic transmissions also get postponed inevitably. And also, merging haptic and video packets result in bigger and bigger packets because of the high data rate of a typical video stream. And on a wireless channel, collisions are quite common. So bigger packets colliding means longer collision, leading to wasted bandwidth. So one solution is to avoid merging of these two streams and separately queue up haptic and video streams at the MAC layer. And based on this, one can come up with efficient link layer or MAC layer transmission scheduling algorithm. So what we want is this, where we have two different queues for haptic and video streams. So we came up with this algorithm called VITALS, that stands for Video Tactile Latency Scheduling, where the idea is to separately enqueue haptic and video streams. And since the video frames are typically large, and transmitting them in just one go would lead to clogging of the bandwidth from the standpoint of haptic streams, we also fragment video streams, and then we also fragment video frames and then apply some sort of thresholding. So it clogs the channel minimally and paves way for seamless transmission of haptics. Without really getting into technical details of this, I would just like to present one particular result where we look at the haptic latency as well as kinematic latency. And VHMux is a state-of-the-art multiplexing protocol that we are directly comparing the performance of VITALS with. And we are only comparing plots that have the same color. So basically, as you can see here, kinematic latency due to Vitals algorithm is at least 50% lower than that due to state of the art, which is over here, which is already a major improvement. And we also see a significant improvement in the haptic latency as well. So all in all, we have reduced the round trip latency of Wi-Fi by about 50%. And this was just a naive implementation of Vitals. We also have an optimal implementation of Vitals that also takes care of a few more things. And the optimal Vitals has resulted in latency reduction of about 80% in comparison with the state of the art. So now moving on to the measurement tools. How exactly do we quantify tactile internet performance? So here is a plot that Dr. Venkatesh Prasad, who was scheduled ahead of my talk, was supposed to present. So I was just thinking I can pick up from wherever he left off. But the idea of this plot is that there is a means by which one can trade off reliability for latency, which essentially means as soon as you transmit less and less number of packets, the overall latency goes down. And we came up with an algorithm called NOBUS that stands for non-buffering scheme, through which we demonstrated that by dropping more and more kinematic packets and with its deployment shown over Wi-Fi, you can reduce the overall RMSE or root mean square error and have the telerobot precisely replicate the human movements, despite a lot of self-induced unreliability. But now the question is, how much of samples are you willing to lose to cut down on the latency? Because there has to be a threshold beyond which the human starts to notice the effect of dropped samples. So it's not clear what exactly that boundary is. So it's right now very hard to quantify what exactly should be the reliability or what exactly should be the latency requirement of tactile internet applications. Or in other words, let's say we were given two different networks, one with 3 millisecond latency and 90% reliability, and the other with 5 millisecond latency and 99% reliability. We don't have a concrete way of saying which network facilitates tactile internet applications better. So the essence of tactile internet that results in such an uncertainty is that different applications demand or feature different sorts of motion. For example, a telesurgery, which involves very fine or micro scale operations, are typically have low velocity of motions than something like a VR game with haptic feedback. So fast motions require faster feedback from the other end, which means the tactile loop has to be pretty fast to give or to satisfy good user experience. And what exactly qualifies as a good user experience is very dependent on the type of motions that the human generates, which means it's dependent on the underlying kinematic or haptic signals. So how do the existing network quality of service metrics like latency, loss, and RMSE capture this? They don't really capture this dependence on underlying signal at all, because a network is, when you talk about a network, we usually say X amount of latency and X amount of losses, which is really oblivious to the underlying kinematic or haptic signal. On the other hand, if you take a root, sorry.
Sorry to interrupt, Dr. Vineet. Actually, Professor Manivanan has a class. Could you please wind up in another 2-3 minutes?
No problems. That should be fine.
Thank you.
Similarly, RMSE or root mean square error also loses out on capturing fine-grained information between sensed and reconstructed. And there is another class of metrics called quality of experience, where you collect mean opinion scores from users, but this is very cumbersome and time-consuming. And there are also some objective metrics which are based on RMSE, and hence they are also unable to accurately quantify tactile internet performance. So in order to circumvent existing shortcomings of the metrics, we come up with our own solution called effective time and value offset, which capture the fine-grained mismatches between sensed and actuated signals. In the interest of time, I will skip over the technical details of ETDO, and I will move to the final part, which is signal reconstruction. There is a standard signal reconstruction technique, which is as soon as you receive a packet, just play it out in the interest of low latency. And looking at this time series, if all of these packets are lost and this one is received successfully, playing it out immediately results in jerky motions, which degrade user experience. And in order to minimize the negative effects of the network, we come up with an adaptive offset framework, which contains the mismatches between sensed and reconstructed signal based on what we call imperceivable signal errors. I'm just going to skip over the technical details of this. So the idea of adaptive offset framework is to slow down the motions of remote robot to make sure the ill effects of network are masked. And we show a significant improvement of adaptive offset framework over the standard reconstruction. To wind it up, tactile internet unlocks a whole new world of applications. It also provides a great playing field for new research. I only touched upon some very specific aspects of tactile internet, but this is a very multidisciplinary domain, and it involves a lot of other aspects as well that are mentioned. So I would now like to conclude my presentation. Thank you so much for your attention.
Thank you so much, Dr. Vineet, for this enlightening talk. Any questions from the audience? If there are no questions, then I would request Professor Manivannan to kindly give us some further details onto haptics communication and the associated protocols and applications.
Excuse me, Prasad here.
Yes, good afternoon, sir. Sir, actually, Professor Manivannan could not earlier connect. So he'll take another 20 minutes and followed by that, we'll connect you. Hope that's
sure. Not a problem, because the time that was
yeah, it was supposed to be yours.
2:40. Okay, no problems.
I'm so sorry. Give us some more time.
No, it's okay. It's okay. I was held up in ISRO, so that's why.
Okay. Thank you.
Yeah, no problems.
So, good afternoon all. Am I audible?
Yes, sir, we can hear you.
Yeah. So, stop the video. Video is not ready. I'll go without the video. So we have Experiential Technology Innovation Center in IIT Madras, which is now including the Haptics lab as a part of the lab. So I'm going to briefly discuss about the haptics related work and specifically the measurement of the experience that may be useful for all of you who are working in the 5G. Although Dr. Vineet has now given a very detailed presentation on how do we measure several parameters for 5G internet, I'm going to talk about now some of the very important concepts which I think everyone who works in tactile internet should be aware of it. Next slide, please. Next slide. Yeah. So although AR, VR, and the haptics is all promising, there are some misunderstanding. My idea of in the next few minutes is to clear up this certain doubts which may be now very important for all of you working in the 5G. Next slide, please. So, this we can skip. Yeah. So in the entire AR, VR, or haptics or 5G, the experience is very important. Although we are talking about so much of technology, we tend to get lost in the technology details. Whereas the main focus should be on the person or the user who is experiencing it. So experiential, how do we measure the experience? The quality of
Sir, your voice is
experience.
very low.
Oh, is it the voice is very low, is it?
Yeah, better. Thanks.
Better? Okay. So I was saying that how do we measure this experience? In the last presentation, Dr. Vinith is talking about the quality of experience, and that is actually subjective measure. What we wanted to do is, in the next few slides, we wanted to see whether we can quantitatively measure these experiences. Next slide, please. Next slide. Yeah. So the main focus should be on the user experience, user perception, and therefore we emphasize on the psychophysics. That's the entire one semester course which I teach in IIT Madras, which is very important for measuring these experiences. Can we measure experiences? That too, no, that too objectively, not subjectively, right? Next slide, please. In the virtual reality or in the haptics, most of the times people are worried about the immersion. But the another important concept of virtual reality, which is interaction, is left out. This is where the 5G internet comes into picture. The interaction is nothing but haptics, although we call it as an interaction. And I believe the entire interaction is nothing but a haptics. Next slide, please. Next slide. Next slide. Yeah. So in our haptics lab, we propose that even our human brain is shaped by the way you use your hands. It is not like the Darwin's theory says that the brain is evolved first and then your human hands evolved later. It is the other way around is what we propose. There are a number of evidences coming around saying that the way you use your hand is what decides your human brain. So there are few the terms which I want you to be now acquainted with. 5G, you're talking about tactile internet, but the word tactile is actually is very, very narrow. I believe it's a misnomer. It should not be used as a tactile internet. The reason why I'll tell you is now after explaining this particular slide, I would like all of you to focus on this particular slide, which is very important to clarify the reason why it should not be called as a tactile internet. The sense of touch. Touch is actually, it is not just a sense of touch. Touch is sense of touch plus our motor systems together is what called the touch. The sense of touch, which is half of it itself, has four different main modality we call it. This is sense. Tactile sense is only one of them. Now, temperature sense, pain sense, kinesthetic sense, all these four senses together is called the sense of touch. In the tactile internet we are talking about, which is I consider is a misnomer, it talks about only the tactile sense. Tactile sense is actually a passive sense. Can you go to the next slide, please? That sense of touch is actually can be considered as a passive sense or the active sense. You move your hands in order to feel the textures, then it is active. If some object is falling on your hands, then it is a tactile. So tactile is passive, active is now using the kinesthesia. So I think the 5G tactile internet is talking about the active haptics. It is not talking about the tactile or passive haptics. Therefore, tactile internet is the misnomer, is what my suggestion is. Next slide, please. Therefore, we define haptics, which is pertaining to both sensing and manipulations together by the humans, the machines, and in virtual reality, in virtual real environments and teleoperated environments. And that should be between the human to human, human to machine, machine to human, machine to machine as well. Okay. So this is a very broad definition of our haptics. Next slide, please. And in fact, we say that now before even the vision based on touch or tactile sense. Without the tactile sense proper, the vision cannot work. Something about 10 years ago, we produced this work on the somatic sensation of vision, why vision and is not the most important sense, touch is the most important sense. In fact, touch is the fundamental sense from which all other 4 senses emerge. What is important for you who are working in the 5G internet is now how do we measure this experience? How do we measure the sensation? How do we measure the manipulation? And therefore, now quantitatively do all these measurements. Next slide, please. Next slide. So in our lab, we have done several of psychophysical experiments and measured several quantitative measures of this as experiences for tactile systems separately, for kinesthetic systems separately, for motor systems separately, and then combinedly for haptic systems separately. Each of these numbers are given over here, and these are very few sample numbers. This is given is only for the finger pad. In fact, we have the number for the entire body. This is what we use it to design several haptic devices, not only haptic devices, VR systems as well. I would like to highlight only one and particular parameter, which is very important for 5G internet, I guess. So yes, here one particular point for the tactile system is that we need the 1000 Hertz update rate so that we don't feel the vibration. Anything that is vibrating at 1000 Hertz, we don't feel it as a vibration, we feel it as a continuous sensation. And that is what decides the tactile internet or the 5G internet. That we need to measure, ensure that 1 millisecond delay so that we don't feel the vibration. But I'm going to show you later some of the experiments we have done that ensures not necessarily 1 millisecond delay. We can our human mind adapts to the several delays up to hundreds of milliseconds. Next slide, please. So we call this as a perceptual engineering. How the latency in our inherent latency in our brain, we get adapted to it. Next slide, please. So many of you may have seen this Apple phone haptic engine, which is designed to give you a very sharp haptic feedback in the latest iPhones. I'm very glad to say that this is designed by our students. Next slide, please. In the internet, since we are talking about the 5G internet, we need to talk about the throughput, bandwidth, and with all the latency. So before considering the latency, we consider the throughput and found out that there is a scaled movement from in the internet, and at what scaled movement the throughput is maximum. We found out that 1:3.3 is the scale movement. We use some of the very standard performance measurement techniques such as the Fitch law. We use a simple vacuum tablet to measure the hand-eye coordination. This we extended to the virtual reality later, and we in fact did it in the micro scale as well. Instead of 1:2 or 1:3, we did it 1:1, 0.5, 1:0.3 at the micro scale also we did. Next slide, please. We also did check that our performance actually reduces when we move our hands in the augmented reality. In certain cases, when you see your hands as well as the virtual hand, real hand as well as the virtual hand together, your performance actually reduces. So irrespective of the delay, irrespective of your the environment, if you happen to see both your hands, real hands and the virtual hand, the performance is delayed. This we call it as a virtual kinesthetic conflict, which is very important guideline to avoid seeing the real hand in the augmented reality. Okay? So the next slide, please. This graph shows that now the performance actually reduces in 3 different conditions. Next slide, please. Next slide shows the scaled down movements instead of scaled up movements. Again, there are some particular scales where we have the optimum throughput. Next slide, please. We also have similar to the visual, we have the tactile circuits or haptic circuits, which is about 5 milliseconds, where we briefly stop before we go to the next point where we can acquire more information, just like visual circuits. Next slide, please. So this is very much relevant to your 5G internet. In the context of 5G internet, we did this experiment about 20 years ago. We call it as a tactile internet. Between MIT Touch Lab and the UCL London, we have the 2 phantoms, and we wanted to lift a virtual cube. This virtual cube can be lifted only if both the people apply equal amount of force and then lift it. So with all the latest internet 2 and least number of routers between MIT and the UCL London, we could achieve this, and this was a very big media hit. But the latency was about 200 milliseconds. We could actually with 200 milliseconds, with all this internet, latest internet at our disposal, we could do that because the human hand itself has a latency. Can you imagine, from the time a stimulus is given to your fingertip to the time the signal reaches your brain and then come back to your fingertip again to move the object, it takes about 200 milliseconds. That's a latency. Therefore, this latency may not have large effect is what our suggestion is. Next slide, please. Recently, we have experimented this concept at in a typical simulation setup, in a telemedicine kind of setup. Between 2 phantoms, we simulated the latency. We wanted to find out at what latency our performance actually degrades. So, of course, the 1 millisecond latency is the best thing. But now, because of the internet delays, what is the latency now we can get away with? So the x-axis shows in this graph, first graph of latency, and the y graph, the J&D measures. We measured with different latency. What is J&D? J&D is actually a measure of your experience. Right? Let us say, without getting into the details. So our J&D, the measure of experience, doesn't degrade until 180 milliseconds. So with 180 milliseconds, our J&D degrades only 5%. 5% is usually is a error of measurement error in any way. Therefore, it doesn't really matter, is what now our papers, recent papers, which we published recently, 2018. I request you to go through this experiment. So in India, we have recently designed this haptic device. Next slide, please. Ensuring this latency. It's a 6 degree of freedom position sensing, 3 degree of freedom force feedback, because of the lockdown and because of this getting the devices is difficult. We have designed ourselves, and it is now available for commercial systems where this latency also can be taken care of it. And next slide, please. All this with latency. Latency means it reduces the stiffness of the object we feel in the internet. So how much latency actually leads to the stiffness perception of the object which we have published. And we have also come up with the ideas of how do we increase the stiffness of the object in a haptics experiment. Next slide, please. we also have displays, the screens, the laptop screens or the desktop screens become tactile, meaning you can touch and feel the textures what you see over here. We have some methods of converting real laptop and the computer screens where we can get the tactile feedback. Again, this can be useful along with 5G internet. This can be useful for the retail market, where before you buy things in the Amazon, you can actually touch and feel and buy things. Next slide, please. So because we understand haptics and tactile, just like a visual illusion, there are tactile illusions as well. This we can now make use of it in order to compensate the latency, in order to compensate the network delay and the other reliability as well. This is what we have proposed in one of the recent papers. We call it as a power law based out of the body tactile funneling for mobile haptics. Next slide, please. These are the equations which is competing with the Disney and Google algorithms. Next slide, please. So in this experiment, we not only give the get the tactile feedback on the body, but also we can get the tactile rendering out of the body using these illusions what we have done. Again, if you're interested, you can go through the publications recently. Next slide, please. For all tactile internet, hand tracking is very important. And in the presence of the latency, how do we track the hand, predict the hand using the AI algorithm is what we recently published. Next slide, please. Using these technologies, we have made several medical simulators. Since I'm a part of the biomedical engineering, we have made several virtual reality based medical simulators. One of the best global market simulator is the in vitro fertilization training simulator, where you can harvest the oocyte and then make an embryo and then put it back, all using the VR and the haptics. And this product is hitting the global market now. And the details of all this medical simulators you can see in our channel called Medical Haptics. This is our startup company. Next slide, please. This is the environment in which the IVF training simulator is done. The ultrasound image, what you see, that's also a simulator as of this simulator is concerned. Next slide, please. We use these technologies to do the stroke rehabilitation as well. Again, the latency and the reliability can help in some way to improve the rehabilitation compared to this traditional rehabilitation as of now in the hospitals. This we have demonstrated in our collaborative institute, Sri Chitra Institute of Medical Sciences, and we found out that this rehabilitation with the haptics and now VR is much better than the traditional rehabilitation. Next slide, please. These techniques are very much in need now for social haptics. Since we are talking of the metaverse, so we are talking about the mobile. 5G is going to come maybe in a couple of years, or right now in India, but not to the every masses. It is going to take 2 years or so, right? Meanwhile, how do we bring the haptics to the masses is what we are working on now. Irrespective of the delays, how do we create this experience? And then finally, this is a final topic I'm going to touch upon. Next slide, please. We have a consortium to create to make a big dream for our Indian government. Just like a IT corridor, we want to create a virtual reality corridor in the next 20 years. Maybe when we celebrate our 100th Independence Day, 25 years down the line, we all want to be known as the virtual reality corridor for the entire world. So towards this vision, next slide, please. We have we have designed now virtual reality courses to all the engineering colleges teachers. Next slide, please. Next slide. Next slide. Next slide. We have a consortium in which now about 230 virtual reality companies are there and to work with us to realize this dream. Next slide, please. Yeah, so there are several specializations we are looking at. We are looking at the automotive vertical. The next slide, please. Education vertical, medical vertical, building vertical, media and entertainment, skills, military, space, ocean, fintech also we are envisaging. So as a basis of all these things to realize this dream, what is needed is to train our youths in quality virtual reality systems. That's what our focus as of now. So with that, I thank organizers to in giving me opportunity to talk about our works, and then I wish you good luck for your workshop. We'll be happy to help you in any way we can. Thank you.
Thank you, Professor Manivandan. We shall take up questions in the end. In the interest of time. Thank you so much.
Bye.
In the interest of time. Thank you, sir. Thank you so much. I would now like to introduce our next ITU expert, Dr. R. Venkatesh Raman. Just a moment. Is my screen visible?
Yeah. Now I'm speaking, so you should be able to hear me now.
Yes. Good afternoon, sir, and welcome. So Dr. R. Venkatesh Prasad is an associate professor at the Embedded Network Systems, Delft University, Netherlands. He did his PhD from ISC Bangalore. His area of interest include haptics communication, IoT, cyber physical systems, energy harvesting, and he has published his research in reputed international journals and conferences. I now request Dr. Prasad to kindly enlighten us further in the area of edge computing and haptics communication. Welcome, sir.
Yeah, thank you. Are you able to see my screen?
Yes, sir.
Yeah, the full screen, right?
No, sir. Can you, sir, click on the display setting and change the display there?
Okay, that's what, because I was not too sure about it. That's why I was asking. Yeah, can you share one? Sorry, not this. Screen 2, yeah, that's why. Okay, now you are able to see the full screen?
Yes, sir.
Okay, great. So let me move fast. I do a lot of work related to embedded systems, including a bit into space. So probably most of the next frontier is about space and tactile internet. The whole thing that we wanted to talk about is about the last mile communication. And what you see on the screen now is Jeff Bezos. You could see that such a highly sophisticated machine is what you need to build to really execute some of the small tasks that he's doing now. It is also important that you need to interface with lots and lots of sensors at the edges. So I'm basically concentrating much more on the last mile. It stopped. Okay. So the work that we are doing at TU Delft, along with Vineet, probably he spoke about some of the things that he's already working on, is to really make tactile internet without really looking into the network. So what are the things which are best done at the edges? Let me move forward. Usually what they say is you require 99%, 99.59 basically the reliability, and people are talking about 1 millisecond, 10 milliseconds reliability and things like that, right? The other aspect is also the bandwidth, because you have so many sensors that you need to connect to get really fine-tuned skill transfer over the internet. Of course, you know already about some of the important use cases. You have lots of automation things there, and then you have also the space, basically tele-repair and gaming and e-commerce, and of course the celebrated use case is telesurgery. So the goal, at least for us at this point of time, is to come up with some sort of a generic framework, and also the interfaces to provide the touch feedback, and to try to see how latency could be really reduced, at least on the last miles. And I will also show some of the things we talked about, some sort of setup. We are not into really huge test beds, but as you know, in a university, what we do in a lab on a experimental table. So we published a paper sometime back from my group, is about a test bed. So wherein we have some of these tactile devices and also the sensors, and then we try to see how we can implement a simple test bed, and we concentrated on the last miles because you don't have a good amount of control over the core network. Some of the things that we tried to do was you could see that we have a virtual environment, and we use these Falcon devices to implement some of the virtual entities where you can get the feedback, the force feedback also, and you can experiment introducing various amount of network infirmities. Here is one simple video that tells you what will happen with respect to network delay. You could see that with network delay, and yeah, you already see that this ball that is trying to push the devices, the blocks, is already giving lots of problems for the user. It's already becoming unstable because of the network infirmities. So we used Chai 3D in this case. So we are basically shifting now to Unity. So the challenges are like how exactly, first thing is to find out what are the infirmities, what are the difficulties, how to really look into the service as a whole because of delay and packet loss. So you could also see that you see easily the subjective ratings are so bad when the network is congested. So we need to really look into the perception and metric, and also how do I compensate for these delays, right? So the next thing is about building a prototype. So we assume that there are network function virtualization as well as software-defined networking that can provide really guaranteed performance in the core, so that we can have an emulator which can really insert whatever the conditions, network conditions that we want to do, so that we don't really need to worry about what will happen inside the core network. So that is one thing that we have taken care of. So then comes the problems and the issues, challenges with respect to the last miles. So what we, at least our design philosophy is that we think that Wi-Fi is going to stay, and newer versions of Wi-Fi is coming into market, and there are already lots of improvements, and also high frequency communications are already getting into this sphere. So wherein you have no problems of bandwidth at the edges. So that means you need to really worry about, so what will happen if you want to really connect the sensors, multiple sensors, and on the other side, actuators to the access point. So we took Wi-Fi to start with, and then we started exploring things. So here is a simple demonstration, and which we did over internet, but the distance was not more than like 12 kilometers between Rotterdam and Delft. Probably you have heard about Rotterdam being one of the second or third biggest port in the world now. So we used a simple glove. It's called Sense Glove, and then it produces data only at 60 hertz. So you could see that the sensors are also not that really well built for the applications. And the robotic arm is a simple limited degrees of freedom, and also it's not too high actuation speed. But we could really get good amount of insights into what will happen, or how do you feel when you do things over the internet. So Sense Glove was in Rotterdam, and we have the actuator in our university building. So so this is the glove. We are working on making this glove much more fast. So there are a few things that we are doing. So now we connected this with Unity, so that you can really get the virtual environment and rendering in the virtual environment. So maybe let us move. Very simple things that we did with our students as the workforce to also make things really customizable. So this is the video where you see how 2 fingers that we built again is working with the Sense Glove. We have an advanced version of it, we are still experimenting and working on it. So you could see the force level that we are actually also mentioning it here. So you can actually hold different objects. That's what you could see here. A big dice that see the separation between the 2 fingers. So that is the force that you're basically giving as a feedback to the user. And also holding the small one, see the separation between the 2 fingers with bigger and smaller dice. Okay, so the last mile, I will try to provide another small piece of work that we did, and it looks a promising one. Recently it was published, and also we have some simulator code that we have shared on GitHub. Basically, my colleague Vineet Gokhale's code. So the idea is that we have really a very high bandwidth last mile communication that we have, for example, Wi-Fi 6, Wi-Fi 7, and others. So can we do something better and evaluate the performance, and then, of course, improve the performance, right? The other simulators that we try to use were not really complete, and so that's why we actually built this whole system. Something that we found out is that in case if your first packet is delayed, so you will start the delay will start cumulatively increase. So then you are not able to really provide a good service. And also there is going to be some sort of frame aggregation because you are not going to have a different flow for each and every sensed data, because you will be getting very less number of bytes, the sensed information. So you are not going to add too many headers so that you simply waste the bandwidth. So the best thing is to do the frame aggregation. And when you do that, so from each of these devices, the sensors, so you will have to also take care of what will happen to the delay between these the actuators, corresponding actuators at the other end. So we try to find out how effective is the current Wi-Fi, and then how can we improve it further, right? So that is something that we looked into, and then we wanted to find out the trade-off. So how exactly we can think of the reliability and the delay in the balancing between them, and how a user really feels about this service, right? So we came up with a very, very simple technique. Probably it's a no-brainer. The idea is that the trajectories of the movements of these fingers, right? So it usually is not going to be completely random or a Brownian motion, right? So it is a smooth trajectory always, or almost always. So in that sense, we can always, even if we lose one or two data points in between, the trajectory, for example, if my hand moves from here to, let us say here, so if it moves in one direction, you know what is the arc it is going to take, or what is the path that it's going to take. So you don't really need to think of too many things. So it is indeed easy to predict or compensate for the missing data. So as if you know the final point, right? So that's where we thought it's best and easy to drop the delayed packets or the data points, and then take the latest frame, right? So we work with this on the simulator, and to tell you that the worst case latency with no bus was just 1.5 milliseconds. But if you really start putting all these things together, then it's much more, it's going to take much more delay. So one thing that I wanted to, so of course we did for uplink and downlink, the position error, right? So the position error without no bus, you could see that it is much higher. It is because you are delayed, right? So that's where the position error will be much, much higher. But if you look at the number of data points transmitted, of course, because you transmit less amount of data, but the error is much, much lesser, right? So the position error in millimeters is that it's approximately like 1.5 millimeter difference compared to 4.5-ish. Right? So this is published, and then we on it. So you could see that in this video where we compensate even if there is a good amount of let's say delay and packet drops that were introduced. the same setup, which we were talking about earlier. So you could see that there is some amount of issues without no bus, and with no bus, you could really see that things are much, much smoother. And of course, we did user studies. We asked multiple users to handle this. We have not only this application in a virtual world, but we also have multiple simple applications where we can use our tactile device to really see how users feel. So now you could see that the subjective measurement, right? So with the current Wi-Fi, what you see is much, much less over a scale of 10. And these are different people who rated. So it's consistently above 80%, whatever that 80% means. So basically 100% or 10 out of 10 is the normal operation without any delay and packet loss. And compared to that, there is in some sense, subjectively 20% degradation. So we ask the users to feel how it behaves without any network issues. And when we introduce network issues, so how they feel, and with no bus and without no bus. Okay, so I think that was the last point. I'm also, within my team, we are also looking for some collaborations and others in future. I'm happy to be with you all here and sharing a few things that we have been doing. Thank you so much. Hello?
Yes, thank you, Dr. Prasad, for this enlightening talk. Thank you so much. Okay, our next speaker is Mr. Vishnu. Mr. Vishnu, are you online?
Yeah, hi Pimi, how are you?
Hello, sir. I'm fine, thank you. How are you?
Good.
Okay. So Mr. Vishnu is he's an independent researcher and ITU consultant. He holds a master's degree in computer science and engineering from IIT Delhi. And he has a lot of experience in the field of telecom industry and implementing standards. And he has been holding many international granted patents. He was nominated to the Scientific Advisory Board Associate Member of Motorola Networks and IET Future Tech Panel. His work includes coordinating standards initiatives, liaisons with other SDOs, industry bodies, open source and academia, and mentoring student projects and coordinating the ITU AI ML challenge. I would like you all to know that when we opened the registrations, we have received till date 20 plus team registrations. Now, upon the request of industry, we'll be opening the registration for 5 more days. The link will be activated. Mr. Vishnu will be giving us more details about this global round and how to win. Over to you, Vishnu, sir.
Thank you so much. Let me first of all take a few minutes to run through this. So this is the introduction to global round. It was I was listening to the presentations, and it was a very interesting set of use cases, presentations, all the previous speakers. It's quite interesting research which is going on. Now the question is what the students will be able to do with it and how to represent this in a manner where you can win some prizes, no? Like Brejesh explained in the beginning, there is a trip to Europe waiting for you. So how to win that trip, and also how after beyond that there is also this global round where participants from across the world come together and they show off what they have done over the period of this time and gain some interaction as well as learn from each other, and also to win prizes and certificates from ITU. So thank you so much for the opportunity. What is this Build-a-thon? Build-a-thon is a problem statement. It's under ITUM challenge. We in India, we are offering this in collaboration with IIT Delhi. Brejesh has been our long-term collaborator in association with the Indo-EU Partnership Project, which is sponsoring, as well as TSTSI. So thank you so much for all the collaboration. We would like to make sure the teams from India win, right? So that's why I'm here. So the Build-a-thon is a proof of concept problem statement. We would like to build these use cases, whatever you heard, the exciting use cases, whatever you heard, and then build it up into a design and an implementation where you can show off to the world. So it's a common open platform, and it is also a POC development activity. It is hosted by Focus Group Autonomous Networks, and I will give you the link to the GitHub, and I will show you how to register. All right, let me quickly go over to who can participate. It's open to anybody. Participant could be a student, a startup, whatever it is. You are welcome to form a team, submit solutions. We prepare mentoring sessions. I do a lot of mentoring myself, but there are very experienced mentors that you, professors that you heard just now. So they are all potential mentors. You already may be talking to them. We also have reference code, which I will show you in a bit. So what are the tasks? So suppose you are registered, and now what are the tasks? So first of all, you have to register. This is the link for registration. I will put it in the chat window, and pin me on. We'll have these links after this presentation is done. You can, of course, introduce yourself, say hi to other participants across the world, and if you have questions, you can ask in the discussion forum. You can select a use case. You heard many interesting use cases just now, so please select one of them and draw a design. I will show you how to do that. Upload that design to GitHub. Use the reference tool sets to demo. Brejesh talked about the invitation to go and work in the lab, to test in the lab. That's a very exciting thing. Don't miss that. Okay, so then this is the timeline. Registration is open. It closes a long time to close, but India, please follow instructions from Pimi. Pimi is the boss. So if she says 5 days, 5 days. Okay. So, but we have time. Please register. I will show you how to do that. The submissions, 28th October is the submissions deadline. Please submit by that time. We also have reports and a grand challenge finale that is coming in December. That's completely online. Many countries participants come and show off present their solutions. And that is a very exciting place. If you make a submission, you will get a certificate. If you win, you get $. Then during this, we had a kickoff workshop. There is a link to this kickoff workshop also. I will, this slide has already the link. I will also put that in the chat window. So how to win prizes? So we have to be active in the GitHub forums, and you have to write this design according to design the use case like what I will show you now. You have to create a demo of the video, upload it to the GitHub, extend the reference code that we have. You have to extend it, show that it works. Ideally, testbed is a very good opportunity to do this. You know, your demo will look real, and it will look something which does something. No, so that is the opportunity for you to use the testbed, take a video, and upload it to the GitHub. That's the way to win. These are all secrets. Don't tell anybody. Okay. So then we map it to standards. You can use HC standards, ITU standards. It doesn't matter. But map it to standards because we are basically a standards organization. We would like to show that interoperability matters. Okay. So we encourage you to map it to standards, and also whatever you do, automate, automate, and automate. So you can apply machine learning, you can apply human learning, whatever you like, but apply it and automate the use case that you are working on. Then you can also look at publishing Jupyter notebooks. There is opportunity to publish after it. Professor Brejesh has already published a paper last year in the collaboration we had last year. He and colleagues have already published a paper in ITU journal. It's right here. Then let's look at some important aspects of the reference design. So we published some reference design that I will give you the link. It's already there in the GitHub. This reference code and design, participants are free to extend it. They can use any tool, but please make sure that the reference queries given here will work. So then we can be all in the same page, so to speak, right? So the design, those of you who have done these designs know that there are many ways to draw the cat, right? You can draw it all black, all jumping, etc. Right? So there are many ways to do the design, but make sure at the end there is a demo which implements the design, and you are able to justify the design. Whatever you have done, you are able to justify the design. That's what we expect you to do. These are the reference queries. I will show you how it works in a bit. A few minutes, that's it. So there are many ways to query, you know, the cat with black cats, long tail, just joking. So there are many ways to query the database, and these are the reference queries that I have given here. This is a simple example of a use case and the corresponding graph that we designed that we have here. The design you can generate it from the reference code. The use case, I strongly suggest to look at the use cases that has been presented today and going to get present today. Okay, so this is just an example. This example is actually from St. Petersburg University, but you don't have to use it. Use the examples that has been presented today. This is about edge computing platforms and how to do on-demand forecasting, service migration to match the latencies, and you know the drill, right? You heard I will leave it to the experts to talk about it. but you see there are requirements, there is design, and then there is implementation, right? So that's the model that we follow to implement any use case. Okay. So there are prices to be won at a global level. 5,000 Swiss francs wait for you. Don't miss that. There are second and third prizes available also. As I told you, this build your own closed loop is a theme. You today, whatever you heard, starting from the first presentation onwards, they have been talking about closed loops, reducing latency, and edge computing, and haptics for that, and so on, right? So this is the theme that we are working upon. We would like to publish this in a repository. We would like to make reference implementations and demonstrations. That's the aim of what we do. Okay, so then in case you want the GPUs, we offer GPUs. ITU offers GPUs. You heard Brejesh talk about testbed, but in addition to that, if you would like to train machine learning models, we offer free GPUs. That's like free lunch, believe me. So, we offer free GPUs. You can write to me. I will make sure that you have access. All right, so there is a question answers that we can discuss at the end whenever Pimi says, and there is the workshop that I will talk about in a bit. Then I want to show you very quickly the reference platforms and how to register. This is our GitHub, okay? So this is how it looks. Let me put this in the chat window. Give me a second. Okay, so it's there in the chat window, and what you do is to click on issues, okay, and go to new issue, okay, and click register for Build-a-thon. You are not fixing bugs, no, that's my job. So you click on register for Build-a-thon, get started, and you're ready to go. So you can directly access this if you like. You can directly access it. I will put that also in the chat window. Just a moment. I should be able to get a better link for you, no? Right, yeah, this is a better link. So yes, right here. So you can actually use that link to register. Choose the register for Build-a-thon. Please don't choose bug fixing. That's different. So if you click, you will be able to put your team name. Bob the Builder is already taken. You can select the number of team members. You can go up to 4 members plus 1 mentor, and you can put the team member details and tell a bit about yourself if you like. Agree to the code of conduct and submit. That's all that you need to do to register. All right. So that's what you do to register. Let me quickly show you the reference notebook so that you're familiar. You go to this one, that is our reference notebook. I will put that link as well in the chat window. Let me see. All right. I'm probably putting in not for everyone. Huh? So let me just repost it. Hang on for a moment. I know Pimi will take care, but let me do it anyways. So right. So if you see here, this is our reference notebook. You can click on open in Colab, single click, it will work. And you can run this in Colab as well. It has 40 use cases built in, and so there are 40 use cases built in. You can see here the 40 use cases. You can run this. This is a notebook, so you can run it cell by cell. And you can see here there are 40 use cases that are already built in. But you don't have to use this use case. You can use the use cases that is being discussed today. And what do you get when you do this? You will get a graph database which shows the design in a nice manner, and you can actually look at the graph design of in this tool. So if you follow my notebook, then this is very easy. It has all the details. You have to just click and follow. In Colab, you can execute it free of cost. Everything is free of cost, and you will get this graph. Now, this graph is too complicated because I have too many stuff in it, but you can actually run it use case by use case and get a simple graph here. For example, you can get based on one use case if you like. You can actually find out all nodes which has edge computing in it. So that's the theme, right? So you can find out all the nodes and the relationships which has neighbors which has edge computing in it. So that's also possible. And once you have this, your design is done. Please submit this design and then go on to coding. So you have requirements, design, and the coding stage. So that's what you do to complete this submissions and win this $, and the prize that we talked about. So I covered. Let me also give you the ITU use cases in case you want. But I have a feeling that the use cases that we talked about today are actually much better than what I give you here. But in any case, if you like to look at some examples, it's here. And also, if you want to map it to the reference code, that will also be useful to map it to the reference code. We also have a Slack channel. You can see what others are doing in the Slack channel. That is also there in the chat window. You can join the Slack channel, and we are also putting a lot of effort to make sure that the Build-a-thon actually gets a lot of help from the participants, get a help from the Slack channel. I am very active. We are also having a bot which will help you as well. If you have questions, you can ask in the Slack channel and we will respond. So that's it from my side. I hope I am on time. Thank you so much. All the best, and see some of you. I hope to see some of you in the Grand Challenge. Over to you, Jimmy.
Thank you so much, sir. I would request all the participants to please continue, stay connected. We'll be back in another 10 minutes after a short break. Thank you. Good evening, all. Now we're over with this tea break. Our next speaker is from the industry, Mr. Chandan Singh. He's present here at IIT Delhi. He has more than 6 years of experience in the area of machine learning and computer vision. Can you see your screen? Is the screen visible, Alok sir?
Yes, can you switch the display, please? Okay.
Is this fine? Okay. So we have Mr. Chandan taking over.
Hello, everyone. I'm Chandan Singh, and I work with TCS Research and Innovation. Mostly, my area of work are in deep learning, solving a range of robotics problem statements that is mainly motivated from industry, and using machine vision concepts, AI, machine deep learning, and these are the techniques that we use. So I have around 6 to 7 years of experience while doing that. So I have done my master's from IIT Patna and in communication system engineering. So basically, this will be the agenda for the sessions. Actually, I just want to describe the robotic manipulation aspect from robotic perception, mainly from visual perception. This is not directly related to haptic perception, but certainly the industry where what type of problems we solve, we find that something to solve it completely or in order to achieve the customer objectives, we need assistance from haptic applications. So that's what we are very excited to about this haptics workshop. So the agenda will be like, so first we'll try to introduce about the TCS Robotics, and then some of the lessons that we learned in mobile robotic manipulation from our participation into Amazon Robotics Challenge. I will demonstrate some of the solutions that we have built down the line of years. And then I will just explain about robotic system architecture with how we have using ROS, how we have integrated the perception and other aspects into as a system. Finally, we'll talk about robotic perception mainly from the vision side. And at the end of the session, I will just talk about an introduction about ROS, how ROS is helpful and what is the basic architecture of. Considering that some of us in the audience are students who will be getting an idea, a sense of how to go further to develop into ROS things. So about TCS Robotics, we have around 100 researchers, engineers. We are working in 2 research groups, like in Smart Machine Research Program, which is working mostly for an accelerated deployment and development of a use case, solving customer use cases, making autonomous machines, creating more autonomy to different sectors related to our TCS customers. And also we are another group which is working on cognitive and collaborative aspect of robotics. So our activities ranging from robotic services, consulting, implementation, operation, and also we have created an ecosystem down the line with OEMs, partnership with OEM, system integrator, certification agencies, and also we have partnership with academia like IIT Kanpur, IIT Kharagpur, and IIIT Hyderabad in robotics. So we have publications around 60 and in conferences with patents more than 50. We have also participated in global challenges like Amazon Robotics Challenge, and Express Avatar MBZIRC, which is a drone competitions, Annex Prize, which is a tele-robotics based competition, and Amazon Robotics is a manipulation. So we have these kind of exposure to the robotics development and participation to the community challenges. So now little bit about what inspirations we have got from Amazon Robotics Challenge. So the Amazon Robotics Challenge will consist of two major tasks. One is the pick task, where the objects need to be picked from a shelf, and it has to be placed on a tote or any boxes, which generally we see with the Amazons. And there was another task which is for a store task, where the objects from these boxes need to be placed back to the shelf. So there were lots of challenges given from the Amazon. The constraints were like different type of objects, and the objects need to be trained in a very short span of time. So that was another. Amazon also gave a challenge about design of the hardware and all these things. So basically, this challenge gave us an opportunity to understand about a robotic system, the hardware things, the sensing part, because they have a limitation on the amount we can expend on sensor selections. So we participated very well in this competition. We collaborated with IIT Kanpur, and in 2017 we were able to achieve a podium finish with third position and fourth in the final round. So in this competition, we were actually well ahead with some of the, as you can see that the point tables, we were well ahead with the MIT Princeton, if we tally all the three events. And also we are well ahead with some of the industrial houses like Panasonic, Mitsubishi, and Toshiba. So this was our stepping stone in the direction of robotics, giving that knowledge and understanding about a robotic system. We keep on building, doing researches, trying to solve problems of the industries, and then we are able to create these type of systems. Like we have a bin picking system, we have autonomous robots, mobile robots, we have a bin packing systems. So if you want to understand these systems, like in the top, we have a bin picking system where we recognize an object and then we pick it accurately. So the perception algorithm is so robust that it can detect similar looking objects very accurately. Second object, the right side is an autonomous mobile robot. It is built from scratch with our manufacturing partners. The software and all these things is being developed by TCS, in-house development. We have also a bin packing algorithm, the right below. It is we can perceive the pose of an object, and then we can identify in a confined space. Like you can see the white boxes, it is a confined space. We just wanted to use a packing algorithm that maximizes how we can place the object inside it, so that the packing efficiency would go higher. So these all the solutions are motivated from our clients' requirements, and then we have built it. So moving to in all of the solutions, the core architecture that we followed, which is very relevant to academia as well. If we want to develop a good amount of system or a POC, then these are some of the components that I want to emphasize here. So we build all our systems based on ROS. So ROS is the one which kind of interfaces with the hardware and the softwares. So in the hardware side, we can have like manipulators, mobile manipulators, sensors. We have vision, laser, IMU, and tactile. In the factor, we have different kind of modalities like suction-based, finger-based, soft gripper-based. So these are the hardware parts, and these components need to communicate with one another or with the software using ROS-based APIs. So the idea here is to create either to get an API, ROS API of this hardware things, or we have to create using their own APIs, we have to create a ROS wrapper. So this is the common practice that we follow. Coming back to the software intelligence part, we have robotics controller, which is basically the core mind of the software. Sorry. So the controller can be a state machine based, where how a task can be executed end to end. it is being taken control by the controller. So the controller can be based on state machine, where each and every subcomponents will be as a state, and then the controller should decide which one to call in order to execute a task. The more sophisticated way of doing is a behavior tree based, which is being provided in ROS2 architecture. And sometimes the manipulation task requires a number of complicated processes. In those cases, we require some classical planners like PDDL, Programming Domain Dependent Language. So it's this is also available in ROS as a ROS1 as a ROS plan, and ROS2 as plan sys2. Second as important component is motion planning, like how the robot is going to move its joints or make its movement, so that in order to achieve a task like velocity, acceleration, and trajectory of the joints. Similarly, we have a collision avoidance, like how these joints need to move so that it not collide with any other objects or with any fixed set of static boundaries like walls or floors. Similarly, for mobile robot, we have motion planning as a navigation ROS nav stack that we use, like we see in a previous slide, an application where we build mobile robots. So there we used ROS nav stack. So this is motion planning as part. The third or most important part that has led to the rapid development of manipulation or implementation of these robots in any practical use cases is because of the perception capabilities, be it a vision or other modalities. So in the vision part, there are object recognition, pose estimation, and grasping. These are the three important aspects which is specifically related to manipulation, mostly object manipulations. And then the tools, we can see that these methods can be AI based, using like deep learning based methods and other things. So, and thus one important part that we want to say, if we want to test a system in a bit faster way, then instead of going directly used to the hardware, we can create one layer which is simulation layer, where we can test the software fastly, and again we can say how this stack will be feasible in short span of time. So that's all the architecture we try to follow for all our development, and it's very much relevant for academia in order to develop, create a POC and other things. So now we'll talk a little bit about the robotic perception side. So three perceptions, visual perceptions, we actually try to create, and we use these perception capabilities or algorithms or softwares in our solutions to solve a task. First is object recognition. So we firstly, it's basically to localize an object in a 3D space and then pass this information to a manipulator so that it can go and grab the object and do the manipulation. So initially we used to do like a 2D object detection and instant segmentation on an image plane, then using that information back to a 3D data in order to localize the object in the 3D space. That's the common approach that we used to follow in the beginning. But later on, this method also works very well for a range of applications. But we try to extend this with using a 3D instant segmentation based approach, because in certain cases, a 2D detection results, if we see the corresponding area, the points of 3D points, due to sensor issues, we sometimes don't get those points. So it happens like in the same ROI, we may get points of a different object. So we try to create build a robustness of this kind of system. So we also explored some work on 3D instant segmentation, where the detection or the deep learning approach or methods directly applied with the 3D point clouds. Now, these are a good approach, but the issue is with respect to the computation, because when we need to process that large number of points, then it's going to cost us computationally. So there are methods like farthest point sampling, where we can reduce the number of points to reduce the computation. But it's problematic when there's a huge clutter. In case of clutter, sometimes doing the farthest point sampling reduces the number of points per object so drastically that it's very difficult to achieve the geometry of an object in the 3D space. So So there's a need of object-aware point cloud sampling methods, which can be a method that identifies the point cloud, how well we can sample point clouds from a given data, and how can we use this data, because this is going to be beneficial for a range of applications. So this is a research problem that academia should tackle. Since the perception has been solved a lot, but still there are some cases where there's no solution at all, or a solution which is, but their accuracy is very low, like the shiny reflective machine pass, and scenarios like highly cluttered scenario with small objects, and also with the transparent object. Some works in this direction of transparent object has happened, like nerve-based methods, but yet to achieve a maturity which can be used for industrial applications. About the next visual perception is a pose estimation, like estimating the rotation and translation of a specific object. The application of this task would be to, once we suppose we know an object by object recognition, but we don't know how it is oriented in space. And if we don't know, then if there is a requirement that we need to place the object in a specific rotation and translation, we definitely will not be able to do. To do this, we require the pose estimation capabilities. So like in the top image, we can see that there's an unorganized object. We have, even if we have a model for this object, the detection algorithm will not say how this is placed in 3D. Then we require some 3D pose estimation algorithm, that then we get the rotation and translation, and applying that into manipulation, we can keep it as a desired orientation and position. So initially, the kind of approach that we targeted are like ICP based methods or global registration method like Super 4 PCS. But these methods are pretty time consuming, and they are highly dependent on the parameters. Like if the system works for a certain cases, then if this scenario changes or object changes, then we need to retune the parameters once again to make it work. So currently we are working with a 6D pose estimation algorithm based on deep learning, where we can see that we have a model which we sampled using some sampling methods, and we identify some key points, and then the deep learning architecture tries to identify the object as well as predict its key point based on a network forward back propagation. We are going to train this network. So in this type of approach, we target two things. Once we object detection, and then the pose estimation all together. So another set of work which is very significant for the industry is the need for using realistic data, right? So supervised method, we know that they require labeled realistic data, but since we have an object model here, we just try to use a physics-based rendering, and then we are keep on tuning the neural architecture, so that it would not or use realistic data, or use at least its dependency on realistic data will be very lesser. Now I want to bring attention towards some of the problem statement that is that we are looking very hardly for getting a solution. Like in a retail use case scenario, we want to arrange a shelf, right? So for the retail use case, the number of SKUs is very high. So using this kind of supervised approach does not work, because the number of SKU is in the order of 100,000 or millions. So we require some method which is for category aware 6D pose estimation. So very few work has happened in this direction. So would like to see some of the works happening from the academia in this directions. Second case is like if we have to arrange the object's pose with respect to in a scenario so that it would appear aesthetically good, then we need to have a method which can detect an object's pose with a scenario like wall or scene or floor. And then once we get a relatively pose of this object in a scene, then we can apply it and get the manipulation done in a desired way. Finally, the third, which is very important and very much relative with how we can extend this problem from haptics or target, is to identify the grasp pose of object present in a scene. So for the cases where we have an object model, we can directly label the object's pose, grasping pose beforehand. Once we get the pose of the object in an image, it's very easy to get its grasp points. But suppose there is a case like where we have no idea information about the object. In those cases, we need to identify by looking into the point cloud or the RGB data, what will be the best grasping pose for that type of object. For our work, for our applications, we have used one method which is developed by us, is domain independent bin picking use case, where we use a sampling and filtering approach, where we just a grasp pose, we try to fit it in a RGB image, and then based on the geometry constraint, we try to reduce the number of graspings. And finally, we have a clustering and axis alignment method to find a specific cluster for individual object instances, pose, and also their alignment, so that we can identify the best grasping pose with some heuristic conditions. So using this kind of approach for grasping, we have also worked on to build some methods where we can find the amount of clutter. So, and once we identify the clutter, then we can apply some action to reduce the clutter. So also we are moving in a direction where we use 3D deep learning based methods, where we can use a neural network. We can directly predict the grasping pose on an object, and then we can use some post-processing methods, some heuristics, some conditions, and we can check if a grasp pose follows that, and then we can decide about whether we should grasp this or not. Giving these things, we are able to perceive the environment, identify their pose, but still, in certain cases, when we try to manipulate the object, we are either object are falling from the grasp, or we are not. We actually manipulated object wrong. So in those cases, haptic-based solutions can be beneficial. Haptics can enable us to identify if the objects are falling. Then a control based on how a haptics control we can be built, as lots of speaker has said and going to be said. So we can use something to avoid the slip. So now the key parameters that we look for this kind of solution is like latency. Definitely the algorithm, perception algorithms latency should be lesser than the hardware speed. So once we able to identify things from an image, and the robot starts manipulating, once it comes back after monitoring, before that we should be ready with our outcomes. Secondly, there are computational memory footprint and power consumption. They also need to be considered while building a neural or any deep learning based architecture. And most important aspect is that the requirement for this kind of solution industry requires very high 9 values. So that is very important aspect when we build a solution from these methods. Now, I need to talk a little bit about the ROS architecture. These are very in ROS 2 documentation we can find them, but I thought of just giving a little bit of initial idea about what ROS is all about. So the ROS is basically a message passing system. It, like I previously said, it integrates the component of a robotic system for communication between one another. So the important things in this ROS is like nodes, which is basically the virtual entity that independent from one another. So it's a nodes, and then the name spacing in which they need to communicate one node with respect to another is called the topics. And the message is the data type through which these nodes communicate on the topic. So the methods for communication in this ROS architecture is 3. One is the publisher subscriber based, pub sub based. Second one is the services, and the third one is the action. So the first publisher subscriber is like a broadcast way of publishing. So nodes which are one information which is required to another node, they subscribe to a common topic, and then one which is publishing that information is available to other nodes as a subscriber. Second type of which is a service, it is based on request and response. It is basically one-to-one communication. So the service, The client, any capability that we build, it is kind of created as a service, and there is a client which is asking for the service. It requests for, and the service has to provide it a response, and then it is a one-to-one communication, good for one-to-one communication. Another set of message passing method is like action, where these nodes communicate in as a goal. First, the client requests for a goal, then in the between of the progress, the server keeps on informing that client that it is how it is progressing. So these three different ways of communication. So we use them for message passing and communicating, creating connection with these components into our robotic system. Now, a little bit about ROS1 and ROS2 architecture. So ROS1 has a concept of master. So there was a supreme node which every node has to be connected. But in ROS2, this dependency is being removed. So each node is independent to communicate, having their own set of parameters. Once one node is asking for parametric value to other node, they can directly communicate without taking help of master. So this ROS2 has some other industry required features like security, authentication, and quality. Most importantly, the quality of services, and it has support for multiple OS, which was not there for ROS. Now, towards the end of my discussion, I would like to just give an example of how this ROS infrastructure or the ROS services and clients work in a system. So, for example, in the left, we can see that this is a controller which is keeping track of the steps involved in a process for a subtask. And it say, let's say there is a vision client which wanting a object pose from a vision service. Now this vision service requires image data from sensor. So it asks for vision data as a service call to the ROS driver of that camera sensor. Once it gets service response from the ROS driver of the hardware sensor, then it processes that image in the middle block, and then once it processes completely, then it converts that to a ROS message and then sent back to the vision client, ROS client, in a message, in a ROS specific message form. Similarly, the controller processes this information further for the, like it can ask for the motion planning client to go for the manipulation, or it can store this information into database. So sorry. So that's all for this session from my end. Any questions from the audience, or happy to answer? Yeah. Yes, sir. Yeah.
Pimiji, are you there?
Yes.
Yes. Yes, sir. Yes, sir. Actually, we had some questions from the audience here in the hall. Can you give us 2-3 minutes?
Basically, the ROS architecture, it is basically hard lines in which mode we are getting communication. They are not the intelligent agents, and the information is not tiny. Unlike the receptive field, which can have any kind of data coming from the previous layer.
I'll just open up your
Here, the data type is fixed. That's why, and the name spacing is fixed. Like it's a vision module. Node 1 and node 2 will communicate on with respect to a data type. It may be Int16, Int8, or any custom data type. That is fixed. What between two nodes? And the architecture, because is rigid. Maybe functionally the system has limited number of hardware components or software components, but virtually agents you can have n number of videos. But that will be fixed. Get fixed at the time of building the application.
The bottom.
So in that case, the nodes are fixed.
architectural haptics, and the communication between these nodes. The data.
Since it's a plus of four, dynamic it's moving system. Yes, yes. So I'm using the workshop
So there. So basically, okay. So basically, you are asking about what type of neural network. So like there are three. No. Yes, basically the data modalities for vision perception are three. One is RGB, another one is the depth data, which is the in our 2D fashion, what each point pixel is, how far is the obstruction, and third one is the point cloud. So the RGB CNNs what we are using or everyone is using, and then for point clouds there is an architecture which is MLP based architecture. We call it the standard architecture like CNN. These are point net or point net plus plus. So these architectures were generally used to extract global features from direct raw points. And depth is like just like an image. So these two modalities and these two are type of feature extractor for extracting their features for subsequent layers to make a predictions. Yes, sure. I think that's all for my session. Thank you for all for being so patient. Thank you. Now I would like Swarno to continue from here onwards. Thank you.
I would now like to welcome Mr. Swarnavade, who's a researcher at TCS Research Center, Kolkata. Is the screen visible? Shalok, can you see the screen?
Yes, Mimiji, it's perfectly fine.
Okay, thank you.
Yeah, thank you all. So I'll present on primarily on deep neural networks for embedded systems. I do not have any expertise on haptics or the other fields, but these days these deep neural networks are all pervasive, and I hope that some of this knowledge will be helpful to these activities as well. So I work as a scientist in TCS research, and also I'm doing my PhD in IIT Kharagpur under Professor PPC and PDG. Both are very eminent professors. So I'll quickly start with a few hot topics in deep neural networks. So first is adversarial robustness of embedded vision systems, and then how we design small DNNs, deep neural networks. And these are all automated approach. Nowadays, no one builds DNN, so our DNNs can be generated just like that. And then I'll take one case study, not two. I don't think I have enough time. So if somehow you are forced to build your own DNN, there. Okay. Fine. So yeah, so then we have to handcraft the DNN. So that will be a case study. So I'll start with the adversarial robustness topic. So this is very important, and many people don't know about this because this is not yet very, well-known problem in deep neural networks, but it exists. So the problem is that there are some changes in the image or in speech, in haptics data, anywhere. So people are doing some small changes in this data. And these changes are not human, not something that human can understand. So there are small changes in the data. You don't understand whether, for example, take this image in the second column, which is, the third column. You see a 8 there. At least I cannot find out there is a change. But the deep neural network says this is 2. So this is something that is happening everywhere. And this has become a menace. So it's because not only in images and videos, we can just put a small sticker in a table and that will drive the classifier crazy. So this is what is happening. So we need to prevent this. So the first problem is human scrutiny cannot help. So even if you put a human person in the loop who will check, they will not be able to help because it's not identified by human eyes. So, I mean, an autonomous car can take a wrong turn based on how it interprets a signal, or there can be a problem, financial problem if check reading is bad through a OCR, and the robot can pick a wrong item. And this can be done intentionally. So the problem is like this, that if we consider an input from a real dimension RS and the output RD, then if this is the network n theta, which maps this X to Y, then this multi-class classification problem, if we add something to X plus delta, a very small noise in the data set, then the classes are completely different. So this is the problem. Now, why it happens? It happens because what we do in machine learning is we want to replicate the probability distribution of a natural process. So this is given by this Py given X. This is the conditional probability. So this learning machine, it will try to imitate this and it tries to create something which is given by the classical paper by Vapnik after the Cold War that is known as empirical risk minimization. So I can learn as good as my data. So now the problem is if I have a physical process and if data is coming out of that, it's only giving a partial picture of that process. I cannot get everything. So that is the reason why there are many pockets in the manifolds where there can be a 2 which actually looks like 3, but I did not take that as one of my examples while training. So it becomes an adversarial example. So it's very difficult to handle this. So these are some of the terms that we need to get familiar with. Quickly, I'll go through this part. That is, what are adversarial attacks? These are changing of images, videos, or other signals by human in a malicious manner. These perturbations are often measured in distances. For example, L1 norm, which is a Manhattan distance, L2 norm, a Euclidean distance between 2 pixels, or a L infinity norm, which is, the max. So that's how we measure that whether an image or data has changed. Now, we also measure the clean accuracy, robust accuracy, and different types of attacks. So there are different types of attacks. For example, I told that I can put a sticker, it becomes a physical attack. So it's a black box attack. And then maybe the attacker knows everything about the model, it becomes a white box attack. So similarly, the community is also interested about adversarial defenses, where we do empirical defense or heuristic defense or probable and certified defenses. So this is how we make a model strong. So for example, if we, as of now, we are not facing this, but the day is not far when we deploy something using a deep neural network and it will not work at all because of this adversarial robustness issue. So then we have to use this kind of defenses. So empirical defenses will use a lot of extra data augmentation with adversarial examples. Then heuristic defense does something very heuristic to solve some problems. And then there are probable and certified defenses. Now the problem is that the problem is whenever there is a new defense, then a new attack comes next year, which breaks that defense. And again, there is a defense for that attack. This goes on as a cat and mouse game. So that is why there is a demand for this probable and reverse defense. Okay. Switch on. Can you hear me? Am I audible? Okay. Okay, so the only thing is that for adversarial defenses in embedded systems, we would require very defense mechanisms which are very small and low overhead in terms of size, runtime memory, CPU cycles, so that it doesn't become an overhead. And we don't have anything like that because these current adversarially trained models are huge. For example, a CIFAR-10, if you train on a CIFAR-10 dataset, it takes only 1 MB. But adversarially trained model is 700 MB. So this will not work. So these probable and certified defenses are not scalable. So we have to rely on heuristic defenses for at least 2-3 years down the line. So, I'll just say about our proposition in this direction. So what we did is instead of using an image directly for a DNN, we used an approximation for it. So this is what we do. When we get an image or video data set, we divide that image or video into small patches, and then we extract that patch, and then we cluster those patches into small symbols. And then we create a code out of that symbol, and we name it a code book. So now we again reconstruct the image or the video frame from that data set such that now the reconstructed image becomes a reconstruction of codes, not the original image. So this actually removes adversarial perturbations. Why? Because if you see this graph, then if I have printed the original image which is after attack, so all these pixels which were supposed to be in the diagonal side, these are the original pixels, this is the pixels after attack. So these have shifted in two sides. This is after the attack. But when I do a symbolic transformation that we define, it takes it brings most pixels back because this is trained on the clean image. So, so this is one mechanism that we have given, and we have published a paper in CVPR this year. So, and there is a blog also on this part. So now I am over with this adversarial attack. If you have any questions, you can send me an email also offline. So now I'll move on to embedded deep neural networks building. So nowadays, what I was saying that this embedded deep neural networks, people are not building anymore by hand. So we have something called neural architecture search. So see the line number 2, you provide the data set, you connect hardware or your whatever specification you have, and the DNN will be generated. So if we take any of these examples, ENAS, MNASNet, or DARTS, differential architecture search, and for example, this proxyless NAS, if you can direct connect a hardware like RPI, and it will generate a model for that. And even microcontrollers like STM32, you can connect to MCUNet. You can just download it from GitHub. And sometimes it builds much better models than normal handcrafted models. So this NAS FPN claims that. So it can be used from GitHub. Anyone can try that on this robotics hand also. But I'll just give a brief idea about that. If you use it, it will be good to know what it is actually. So as earlier we discussed that we have X belonging to a real number N, which is the input dimension, for example, R cross 3. And then we have labels Y1, Y2, YK, maybe the 10 numbers of MNIST, for example. So I can train a DNA in theta such that X gives Y. What we want to learn in neural architecture search is I pass X, my data set, my label Y, and my P, which is a performance indicator, and I get a network out. So this is how this works. So what are these PIs? These PIs can be what is the RAM size of my board, what is the accuracy that I want, 90% for example, and maybe something else like what is the number of max, multiply and accumulate, which can give me a proxy for the energy. So this is how this whole thing works. So for example, I can break down an architecture of a network n theta into different layers. We all know these are all feed forward layers or some other architecture. So it can be in N1 theta 1, N2 theta 2. These are individual layers. This can be a convolution layer. This can be a pooling layer. This can be a some other layer, residual layer. So it becomes, and n theta becomes N1, N2, N3, N4, and Nm theta. So now I want to generate this thing automatically. So what we do is we create a state vector, which is, for example, there is a state vector S. This state vector, it looks like this, a vector. This vector, this 2, we can assume that this 2 is a convolution layer. I'm just telling, consider that there is a lookup table, and this in the lookup table, it is told that this 2 refers to a convolution layer. This 1 refers to a termination layer. 3 refers to a max pool. So at any point of time, I just create a state vector, and this state vector represents my whole network architecture, which is n theta. And then there is also a reward function. You will encounter this reward function every time you do anything with reinforcement learning. So reinforcement learning, this reward function maps a particular KPI. For example, the RAM size that I have in my robot, or the processor speed that I have, or the accuracy that is my target to a particular reward. So the idea of a multi-agent system or a single agent system is always to maximize a reward using some policy. It can be a epsilon greedy policy that I'll grab the most rewards at a particular step, current step. I'll also greedily take everything in the future. So if you see the expression for this reward, there is a recursive reward for that. Now, given this state vector, which represents the network and the network architecture and all my KPIs, which is my performance indicators, and the reward function, the NAS works like this. So if you see this episode T+2, at every stage, the designer, which is an automated designer, it creates a network architecture. This 5, 4, 6, 1, 9, these are all number of layers, and not number of layers, something related to the layer names or something that I have created. So for example, this is a neural network which has an initial input layer and then a convolution layer, then a pooling layer, something like that. So that is what the designer has created. And then this is this network that is created, which is expressed by this state vector, is trained and evaluated. And these KPIs are generated. These KPIs are nothing but the accuracy, the power consumption, the latency, everything. This is then fed back to the DNN designer agent. And this DNN designer agent does two things. It sends this information that what is my current state, what was chosen by the reinforcement learning agent, and what is the reward associated that to some deep neural network. This can be a Q neural network, this can be a RL network, this can be anything. Anything which is again another deep neural network. And only challenge for a designer is in the exploration phase when I am taking random decisions. See, in episode T, which is the starting episode, the network was all one. So it was all some layer, some input layer. But that cannot be a good network, right? With all neural network. Then it got a bad reward in A2 step. And it found that if I choose some other state vector, some other design of the network, then I am going to get a good network. So this is how it works. Once this deep neural network QNN or the reinforcement learning agent learns everything, then it becomes very smooth sailing. It can create DNNs easily. Only thing is how much time it will take to converge. Now, this is the other approach, the reduction approach. So I'd say that this is a dead area, but still I'm covering this. So this is the main architecture that came from MIT Han Labs in 2016, the deep compression. The left-hand side has changed a lot. Right-hand side has remained the same over the years. So the context here is you already have a good model for a desktop system. You want to bring it into your robotic arm or embedded device. So we can do some pruning, compression, and some knowledge distillation to make that model smaller. So why I say that this is a dead field? Because it was then when people used to design deep neural networks which were over parameterized. But nowadays, people have no reason to do that. This neural architecture search and other things have created ways with which you can design very compact networks which are not over parameterized. So if there are no over parameters, you cannot prune also. So it's quite simple to understand. So this left-hand side, first what we do is we either prune or zero some number of connection, and then there is a step of quantization where we transform the full precision 14.32 bit weights into a 8-bit int 8 or something that we require. Definitely we will have some accuracy loss here. And finally, we do some kind of coding to reduce the size further and put it into a device. So this is how it works. It's quite simple, and it's also there in the standard library. So we take our DNN class, and in PyTorch, if we go, we just have to import this torch and then call the quantization and dequantization stub. And in the network itself, we have to do this line. X equal to self.qx. This x is the input. Self.q is what I defined here. T.quantization.quantization sub, and it's done. So quantization is that easy. And this pruning is also, I think it's easier. We have to call this API dependency graph, then create a dependency graph with my input size. This is for CIFAR 1, 1, 32, 32. And then we create a pruning plan, which is also something that we always copy paste and then execute the pruning. You're probably you'll get a smaller model, and we can then put it into a hardware after proper quantization. Now, if all these automated method fails, then we have to design DNN by our hand. So that's not an easy thing, but I'll do a quick case study. So for example, this is the MBZIRC challenge that was there in 2020. So robotics team from Bangalore, they were supposed to do a firefighting, the third case, the disaster scenario, where there is a building inside a fire, drone has to go there. It has to detect whether there is a fire or not, and then extinguish that. So that part was very difficult. How to extinguish? They will throw water there on that spot. And we actually needed to find out the location of the fire inside the frame. So and then they came back to us in the Kolkata labs. They wanted us to detect the fire and then tell the exact location of the fire in the frame. So we were given a DJC drone, and we did that fire localization on some images, and we were given an Intel neural compute stick, which can be attached to the drone, and then the drone will fly. And we were told that our model should run on the neural compute stick. It should not go to the drone because drone has many other processes. Its battery will drain and many other things. So that was the scope. So it's very tempting. We could have used directly object detection architecture like SSD. If you see the SSD architecture here, which is a standard, so all this object detection architecture, so this fat part is the feature extractor. So this feature extractor here, it is written VGG16. So VGG16 is a very strong deep neural network. It will find out all the low-level features like age, etc., and then that will help to classify as well as detect the object. So how object detection is done? So these features are then connected to something called detectors. So these detectors have different feature maps, and these feature maps will generate a standard number of detections per class. And these classes, from these classes, we will get only the maximum, most perfectly identified objects only as the output. So this data set is also different for object detection, because here it is not plain image, but an image with a bounding box. So when we get the image, it looks like that we have an image and we have some XY coordinates with that. So this is a very costly kind of data set. Normally we don't get annotated images. What we get is lot of normal images and even some classes associated with that, but not many object detection kind of data sets. So exactly that happened. We did not get anything for fire detection, and so we did not have a good enough, number of annotated data which tells us that where exactly within the frame there is a fire. But there are many images where from where I can build a classifier which tells me whether there is fire or no fire. So what to do? So current object detection model, if you see, it only provides a confidence class per box. So it will not tell you that whether there is a fire or not. It will tell that here is a box, and within that box, whether it detected a fire or not. So you can go check here that this is the loss function of SSD. So all these deep neural network models have a loss function. It can be a mean square error or a simple loss, or it can be a very complex loss like what SSD has. So this XPIJ is one box. It is one box where the fire can be detected, and this loss is a summation of two loss, linear interpolation of two loss. One is a confidence loss, that within the box, what is the confidence of fire? And then the other loss, that where exactly is the box detected, which is a regression loss. It tells me that this is x1, y1, these are the coordinates. So if you see equation number 3, so it tells me that where is the ground truth xy coordinates and where is my identified. So SSD or any other object detector, it gave me a loss function, which is an integrated loss, which is where is my box in terms of the XY coordinate and where exactly within the box, what is the class. And you cannot do anything about that. But we were not satisfied with that, because what we needed is two separate models. One will tell that whether it's a fire or not fire. And then if it's a fire, then only we will search for the object, fire object location. Because as we used only a very less number of images to train the fire localization model, there is a high chance that there will be a lot of false positives. It will take a street light as a fire and then draw a box and tell that this is fire. And then they will lose in the competition. So it's very important to first segregate out the fire images. So, so yes, we could build two separate models, one for classification and one for object detection. First run the classification and then run the object detection. But the problem is the platform that we were given, we cannot run two deep neural network models. So this is a situation where we have to change a deep neural network model and handcraft it. So if you see the architecture of SSD that I showed, it's only the confidence per box. The confidence per class. There is no way to know whether it's a fire, non-fire, whether it's one object or another object classification. So we stitch this architecture in such a way that we have fire images, with bounding box, both can be used to train this. It has one segment which does the feature extraction for both the layers. Then it has something like SSD, which detects the objects, but it also has one classifier associated with that. Now this whole architecture will be trained. Now in the inference part, what will happen is through the feature extractor, the image will come. This is the feature extractor part, segment A. And then if it is classified as fire, then only the object detector will be fired. If it is not fire, then no fire will detect, object detector will not run. Now, this is how we change the architecture. Now, if we change architecture of a DNN, the loss function will also change. So this is how it changed. If you see that I have compared it with SSD loss. So SSD loss, if you see that we had confidence loss plus location loss. We have the same thing here. It's confidence loss and these are the task specific loss. This is the SSD loss, which is a confidence loss and also the location loss. We also have a classification loss, which you can identify from here that this is basically a binary cross entropy where there is a fire or there is no fire. And we also have kept a small variable v new here, new t, which says me that if it's a fire image, then train only this loss. And if it's a fire image with bounding box, then train the whole network. This is what is happening here. This new is equal to 1, new is equal to 0. So you don't need to understand the specifics of that. But the thing that is required to understand here is we may have certain requirements while designing DNN and which requires us to modify the architecture. And there will be definitely cases where in object detection, you will have very less data. You have to do data augmentation, but data augmentation will also not work because you can generate different classes of data, but you cannot generate the bounding boxes. Then you need completely different image. So this problem, many people will face. So then what we have to do is if we change the architecture, we have to also change the loss function. And we have to apply something called multitask loss. This multitask loss, it's very critical thing, but it's very simple also because it's basically a linear interpolation of a variable alpha and 1 minus alpha. So this alpha and 1 minus alpha can be fixed by a domain expert or it can be learned also while training. So in this, we have to just insert our loss function and that's how we design a new network and change the loss function. Finally, the step 3 is when we took this to a hardware, then we had to do some kind of hardware software co-design. The same thing I guess will apply in robotic arm also because it depends on whenever we put something into hardware, there is often a limit of int8 quantization. We haven't seen any exception to that. So int8 quantization results in a drastic fall of mean average precision in object detection, even if with a quantization aware retraining. So it's good to use some kind of automated algorithm which can find out that how many layers if I accelerate in a hardware, what is my drop and come to a basic point where like one speaker told that 90% reliability with 3 millisecond latency and 99% with 5 milliseconds. The same thing we have to do for DLs also. So in DLs, we need to run some kind of algorithms to find out the sweet point that these are the amount of layers that we want to put into the hardware. So that's all from my side. Do I have any more time or it ends? Oh, so I still have some time? 10 minutes, okay. Good, so then where is the desktop? Something happened. Okay, so as I have 10 minutes time, I'll also do the other case study. Maybe I can ask one question. Yeah, sure. Please. Just an observation. Right? The case study is very interesting. So if you use data fusion, I think you have all optical images, right? It is optical sensor. Camera. Acoustic, sorry, temperature sensor. Right? Then you can really figure out whether there is a fire or not. Otherwise, you can put with the image of a fire. You're absolutely right. So now, perturbation that is going to be crossing charge, whether it is hacked or not hacked. Okay. So if I put the image of a fire and you have to apply your perturbation adjustment technique,
that users had made. One is the data equipment part,
Hmm.
and maybe that could be done as a edge computing that we have.
Yes, yes. So we have seen such architectures, like we have seen such architectures where there is a temperature sensor or a K nose which finds the ECO2 level and then augments that with the fire detection information. So they're very good systems. So that is one part. And how it relates to adversarial examples?
So I could put the image of fire.
Yes, yes, yes. Really, that's what is happening. That has become a menace, but it's still not out there. People are waiting when these things, robots, etc., will come out in the wild. Then they will start facing this problem. And there is a huge interest in research community. If you see NeurIP, CVPR, all these things, there is a significant chunk of paper only for adversarial robustness because this is going to come in real fields. Okay, so here, actually, this is the second use case. So here, what I want to say is that we saw the vision part. So similarly, there is on the NLP and speech also. So people often use these encoder-decoder architectures. So these encoder-decoder architectures are, they take some input, they encode that into a small context, and finally pass that into a decoder. Some decoding comes out. For example, here, French to English translation. So now, so basically there is a decoder or encoder RNN, and then there is a context actually. This context is passed to the decoder RNN and output is generated. Now the question is, this context actually helped us to disassociate from the input and the output. So if in the input, there are 3 words, I can have an output which has 2 words also, which is there is no link between the size of the input and the output. So this is a boon, and then this is also a problem. Problem because this context becomes a bottleneck. If my context is very large, I cannot fit it into an embedded system. So something has to be done. For example, this is a transformer architecture where this context is actually a diagonal mapping. But fitting this into an embedded system is a challenge. So I'll quickly do that case study. I'll skip these explainability things. So this case study was, there is a challenge which is known as deep drone challenge, which is given in this BrickKR-digital.ddc. So they wanted to do some kind of, they gives a contest where these UAVs will be listening to ATC advisory. The ATC is the air traffic controller, and they will say that don't go there, come here, this is a demarcated area, now stop, something like that. And the drone has to understand those voice messages and do the navigation. Now, this required the drone to have some capability to understand natural language, and typically this size of these commands are speech output, streaming speech is 400 to 600 milliseconds. These are the commands that comes from ATC. So in disguise, this is actually a Turing challenge where the operator will never understand whether it's talking to a human or a drone, but they did not write that in that challenge. But the challenge for our case was to build a streaming model on the drone, which is different from what exists. What exists is these things. This one from Google, which actually does very good ASR on using a transformer, and that works on fully on full speech signal, I would say. So these are the best models that used to work on different problems in speech recognition. And for example, Google's RNNT and Facebook's, there is a fair output from fair. I don't remember now. This was done long back. So, so the problem is these are all dedicated for complete ASR, speech recognition. But these are not for those 500, 600 milliseconds. Now the challenge was that if I consider only that amount of data, is there any way in which I can reduce these models. So in the image case, we had one problem. In the ASR case, the problem was different. Here, the problem was, it's not a full speech. It's a command, come here, go there, or park here. And based on this domain knowledge, can I reduce the ASR model for embedded system? Can I build a DNN like that? So this is what is the existing state. CTC, it is the, I would say, the main thing of speech decoding. There is an audio waveform, and then we slice the speech features into windows. Then there is an encoder network, and then I just told you it creates a context, passes to the decoder, and for each time steps, it passes one softmax output. This softmax output is 26, all A through Z. A through Z, and each output, when concatenated, becomes some kind of word. And then there is a language model decoder, and we get the final level. This CTC was bettered by RNN transducer. It was given by Google. And this, what it does, it also takes into account the labels that were earlier generated, and they were jointly optimized with the output distribution, and finally the LM decoder, and finally we get a beta set. And finally, now people nowadays, after this transformer, everything is transformer. So this encoder attention and decoder attention together, they created very good speech models. Now this transformer will not work for our case. It has so much huge memory demand that it will not fit into an embedded system. RNNT can fit. It's a very good model. So we also tried to create a handcrafted DNN based on RNNT. Only target was, can I do anything so that this size of the model becomes small, given that I have a knowledge that my commands are also small. These are not very long speech with long dependency. So this is what we did. We created an architecture. I'm not going to explain the maths here. So what we did is we identified through visualization that in these short commands, there are many kind of features. These features are different from I mean, a long form speech. So for example, the breaks, where actually there are vowel sounds, where are strays, all these things are different from a long form speech. So here, if we see that this is a very long form sentence. So these are clearly three parts. A good ASR can detect the three parts in a sentence. But ASR, which is not trained on these long form sentences, it will never understand this part of the sentence. This kind of long sentences. It only, if you see the upper part of the image, it has identified two sections of the image. But there are actually there are three parts of this sentence. But we trained the model on this kind of data set. So here the trick was to create a data set which has only this kind of small commands, small sentences with proper breaks and intonation. And then we created this model, and we found that, okay, so this character error rate is not at all comparable with deep speech, but it works very good with commands. So this is one of the case studies that I wanted to do for the speech part. So overall, any questions? Not this, other projects. Yes, in audio. Okay, thank you.
Thank you, sir. Next, we have Professor Arzad Alam Khirani, who's an associate professor at IIT Bhilai. Professor Arzad is also an adjunct faculty at IIT Delhi. Will you connect?
Yeah, I'll just share my. And I'll use this mic.
Sure. Should I put this on this mic? Okay.
This mic. Okay, so yeah, I can see that my screen is visible. Is this fine? Here you need to do a full screen or something. This is fine. It's okay. I mean, this should be fine. Thank you. Okay, so good afternoon all. I am Arzad Khairani from IIT Bhilai. So for this Build-a-thon, where we are trying to come up with applications for MEC environment, I will give some brief background on our motivation and how we have set up the environment so that the participants can get some information about how the entries should be. Okay? So I started all my talks with this slide. Actually, this I found, this is from 1977, a vision of how computers and communication will converge. And I have found it very interesting. So even at that time in 1977, in one conference, NEC had given this kind of roadmap of convergence in 2000 between computers and communication. We are well beyond that, and we are seeing more and more such convergence happening, right? And that is one of the reasons that we are here for today. So we see lots of exciting advancements in 5G and beyond requirements. We can see that, I mean, most of the people are of the opinion that 5G and beyond will enable tactile internet. We don't have to get into all the details. Lots of interesting discussions have happened today on what tactile internet is. I am here to talk about the use of edge in case of 5G and beyond, because that is what we are trying to leverage here. So if we see essentially edge, so connectivity and compute is what we have already seen in terms of the convergence part. And what we feel is that when connectivity and compute come together, we will have very good control over control in some sense, right? So that's what we are trying to do. You'll see lots of haptics applications. We are essentially trying to do a control of this haptics applications using advanced compute solutions, lots of neural network and machine learning solutions, and the connectivity part. So how does edge appear in the communication path between the end user and a controller? So if you see on the left-hand side, we are limiting ourselves to cellular networks for now because we are working with 5G systems. So these are the 5G base stations. This is where your controlled robot is for us for now, right? In general, if you are looking at a teleoperation kind of scenario, then your controller is running somewhere far in the cloud. So in doing this, for all of this to happen, many people do not realize that there are many intermediate components. For example, the core network of the cellular operator itself and the external network, which we call internet. Right? So this is, I mean, for experts, obviously, this is a very straightforward thing. But in general, if edge is not there, if we don't do anything about this, we are talking about the data path from the robot to the controller and the reverse path of this kind, green kind, right? Which is a lot of delay essentially. And when we talk about delay, control gets messed up because of delay, if I can use that kind of term. So simple solution about edge is that we bring some kind of control or predictive logic close to the end device that we are trying to control. So that's our edge control path. Right? So UE2, so UE is user equipment, which is the robot that we are trying to control. At a very high level, this is how it is. We have seen many tactile applications today, so I don't want to go through the list here today. How are we planning to use or to leverage edge in edge computing for low latency? We have a setup, and this is the setup for which this Build-a-thon is on which this Build-a-thon is around. We have a robotic hand on the left-hand side, which is acting as the user equipment. And we have a haptic glove, which is acting as the remote controller. They are connected via 5G network. And we have inserted an edge where the participants can insert their own logic for edge computing. For example, one thing that we are doing is intent prediction. If the haptic glove is trying to do something, and if the edge computing device can predict what the intent of the haptic glove is 100 milliseconds from now, then it may be able to raise that kind of control towards the robotic hand early ahead of time, right? So that's the kind of lots of such schemes can be thought of when we start talking about reducing the latency in the systems. One thing that I wish to emphasize is that cellular communication standards based architecture for such systems are still evolving. They're a very hot topic. We are with IIT Delhi and IIT Bhilai, we are actively participating in these standards and we are contributing to those. From this Build-a-thon, we feel that we will also have lots of learning from the participants and we will possibly be able to take this learning to the standards. So effectively what we have done, so I'll try to cut short my presentation now. So what we have done in a summary is that there are lots of architecture details. Our solution is HC compliant. All that the participants have to do is build this client app, and we have a very good document which helps the participants write these applications. They just have to write the applications. Everything else we have taken care of already in the infrastructure. So they have to write this application, not worrying about the edge computing part, and also build the application which runs on the edge and the application which runs on the cloud. So these are the three applications that the participants are going to provide us, and we will run it on our edge system. Okay. So there are two applications that we have zeroed in on. One is the force estimation plus slip detection, where effectively the object is being currently held by the robotic hand. So all the experiments will start with the same initial condition. The object may tend to fall from the grip of the hand. So we may change the gravity in the simulation if we do it in the simulations and so on. Then we want to be able to leverage the latency aware deep learning techniques to find if the object is going to slip, right? So we have to basically detect onset of slip. Okay? For this, all the entries will be trained over the same data set, which we will be providing. Second is, this is one activity that we have been discussing about a lot. So we wish to be able to detect the object which is being held by this particular robotic hand. Okay? So that's the information that I wanted to share. Thanks a lot for your time.
Thank you so much, Professor Azad. Any questions from the audience or the participants? Okay, in case there are any queries, we can be contacted via the email ID stated on the flyer. Again, repeating, the registrations would be open once again for another 5 days. So new teams can get registered. I now request Professor Brejesh Lall to please come over for a vote of thanks.
Yeah. So good evening, everyone. Thank you for sparing your time and participating in this particular workshop. I would like to thank all the speakers who spared valuable time and brought very, very fruitful insights to the audience. I'm sure the participants for this particular workshop will have found them useful. I'm really quite happy to hear the kind of work that they are doing and collaboration opportunities that might accrue because of the discussions that we've had today. So, and I'd also like to thank the team who set this workshop up. I want to thank ITU for conceptualizing the Build-a-thon idea and taking it up to the global level. And finally, Vinti, if you would come and read out all the names and formally thank them. You've been quite an important pillar of all the work that's happened here. Thank you so much. Thanks, everyone. Thanks. Vinti, over to you.
Thank you very much for lovely expert talks that we had. We understood a lot of knowledge which came around. I would like to thank, starting with Professor Manivannan, Professor R.V. Prasad, Professor Gokhale, and then of course we have the TCS team. We have Mr. Swarnavade, Mr. Chandan, and Mr. Ayush, and Professor Arzad, who is also coming from IIT Bhilai. And it was an excellent talk. Thank you so much. Thank you very much. Thank you, Mr. Arun Mukherjee and Alok. Thank you. Good day. And bye, Vishnu. Thank you.
Bye. Thanks to Nick.
Thank you, Muni.